तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
So, we shall continue our discussion on memories. We have studied or seen how the static RAM and the dynamic RAM are realized. So, today's class we shall take up another form of memory, which is the read only memory. Okay. So, as its name implies, this type of memory is a read only memory, that is you can, but although it says read only memory, it is not that you can only read from it, you can also write into it in some forms of ROM, which we shall see. But the reading process is the more favorable process, in the sense that it can be done very fast, whereas the writing process is a more cumbersome process in many cases, and it takes a much longer amount of time. Okay, so that is why it is called a read only memory. So, we shall see the different types of read only memories which are available and see how they are actually realized in practice. Okay. The one type of read only memory which is called the mask programmable ROM, this type of read only memory can be programmed once and for all. Okay, and once you program this read only memory, okay, you cannot change it. Okay, so this is in true essence a read only memory. Okay, you cannot actually write, you can write once and for all. Okay, so the basic structure of such memory or a ROM is something like this. So, just like we had in the other forms of memory, you have the rows and the columns. Okay. So, you have the rows and the columns here, and again at the intersection of the rows and the columns you have the memory cells. Okay. So, in this case the memory cell consists of just a MOS transistor, an MOS transistor at the intersection of the row and the column. So, okay, and here you have the load, and this connects to VDD. Okay. Okay, and here you have the outputs through inverters. Okay. So, at each intersection, okay, you may or may not have a MOS transistor. Okay. Usually, in fact, in actual practice, MOS transistor is fabricated at every intersection. Okay. Basically, the gate of the MOS transistor may or may not be connected to the word line. Okay. That is the thing, because it does not make sense to actually not to fabricate a MOS transistor, because the array is fabricated like straight lines. Okay. The lines running vertically and horizontally, and so you have to provide space for a transistor. You cannot have crooked lines. Okay. So, since the space is, you are not saving space by not fabricating a MOS transistor, you actually fabricate a MOS transistor at every intersection, and the gate of the MOS transistor may or may not be connected to the word line. So, these are the word lines, okay, and these are the bit lines, say the vertical lines. Now, what happens is, when the word line goes high, okay, so only one word line can go high at a time. Okay, when the word line goes high, then all the transistors on this column, okay, on this row are selected. Okay, if there is a transistor there. Okay, and if there is a transistor there, the transistor turns on okay, and when the transistor turns on, the bit line is pulled to low, okay, and the output goes high. Okay. So, basically and then of course, so depending on whether you have a transistor here or not, okay, a transistor is connected here or not. If there is no transistor at this intersection, what happens is this bit line is going to remain high, all right. So, and the output is going to be low. So, basically by putting a transistor here connecting a transistor here or not, okay, you have stored a 1 or 0 at this particular location. Okay. The location means the address corresponding to this particular intersection of the word line and the bit line. Okay. And once you have made the chip, okay, once you have fabricated the chip, okay, it is the programming is over. You cannot change it anymore. Okay. So, basically in this case you want to have a certain some storage which you do not want to change over and over again. Okay. Whatever is there once and for all, you want to use it. Okay. For example, you want to make a controller program of some system. Okay. Now you know that this program is fixed. Okay. So, you want it in large volumes, maybe you can fabricate a ROM which contains that program, okay, and then use it, all right. And once you do it, there is no it cannot be changed. That is an advantage to some extent, okay, because if you are programming in a RAM, you may have to keep on change, it may get changed, okay, again, and in which case you have to reprogram it again. Okay. So, that is a mass programmable ROM. So, but this has a inherent disadvantage, is that once you program it, you cannot change it. So, there are other types of ROMs, okay, available, which removes this drawback, in the sense that you have the flexibility of programming the ROM. Okay. That is, basically you can write it, you can erase whatever is stored in the ROM and rewrite into that memory, okay, and then you can use it as a ROM, okay, and again after you want to maybe you want to load something else into that ROM, you can do it once again. So, that type of memory is called a Eeprom, okay, which stands for erasable programmable ROM. Okay. Now, so there are different types of erasable. How you are going to erase that? Okay, we shall see. So, that gives rise to again different types of EPROMs. Okay, and we shall discuss that. Now, the basic transistor or basic active device in an EPROM is slightly different from the normal MOS transistor here. Okay. What you use is in an EPROM is what is called a FAMOS device. Okay. The name of the device is called a FAMOS device, which stands for floating gate avalanche floating gate avalanche injection MOS transistor. All right. So, that is the type of device which you use. I will just draw the cross section of that device and say how it looks like. So, it is just like a MOS transistor. So, N plus P, but what you have here is you have, as the name implies, what is called a floating gate. All right. That is basically this is the oxide, you have this is the gate, all right, and So, this is the source and drain contact, and this is a gate and this is another gate. All right. This is the gate, this is the source, this is the drain. Okay. So, this is the FAMOS device. Okay. Now, you see this there are basically two gates to this MOS transistor, okay, and one gate is a floating gate in the sense that you have no electrical connection to that gate. Okay. You cannot access that gate electrically. All right. So, that is why it is called a floating gate, okay, and the device is called a floating gate MOS transistor. So, basically the symbol for that is you have, all right, it is something like this, which implies the you have a floating gate here, okay, one gate which cannot be accessed. All right. Now, how does this work? All right. What happens is this, you see, basically there is a gate here and here this is the silicon dioxide underneath it. This is a very thin layer of silicon dioxide, okay. And what happens is, now if you apply a source and drain potential, a normal source and drain potential, okay, maybe slightly higher, what happens is electrons will move from the source to the drain, and the gate voltage, if it is made very high, okay, normally for normal what is done is, if the gate voltage is say made plus 25 volts say, okay, and the drain voltage is say plus 5 volts, what would happen is the electrons normally if this gate voltage is higher than the threshold voltage, okay, you have a channel, okay, and electrons flow from the source to the drain, okay, for a normal MOSFET operation. Okay. Now, what happens is, because of the very high gate voltage, okay, in this case some of these electrons, okay, what happens is acquire very high energy, and they have sufficient energy to overcome this barrier, okay, at this silicon dioxide barrier, okay, and these electrons get implanted into the floating gate. Okay. Many of these electrons, because of the very high electric field, okay, because the gate voltage is made very high, many of the electrons which are flowing from the source to the drain, okay, they have very high energy and they get implanted into the floating gate. Okay. So, what happens is, basically you have a negative charge on the floating gate. All right. Now, what is the effect of a negative charge on the floating gate? So, now if this is for programming, okay, you have put a gate 25 volts and 5 volts. Well, normal operation you will have normal voltages, say gate voltage 5 volts or so. Now, what happens is, if you when the electrons are get implanted into the floating gate, okay, what happens to the threshold voltage? The threshold voltage is going to increase, because you have a negative charge on this gate, okay, which is going to result in positive charges in the silicon. Okay. All right. And in order to overcome that, you have to apply a much larger gate voltage on this gate, which is called the control gate. So, you have a floating gate and the control gate. So, you must apply a much larger voltage at the control gate to create the channel, basically in order to overcome the negative charges on the effect of the negative charges on the floating gate. So, basically the threshold voltage is increased, okay, by this process of implanting negative charges on the floating gate. Now, if we come back to this circuit here, in a mass programmable ROM, what you had was you either had a MOS transistor or you did not have a MOS transistor at this. Now, suppose if you consider two transistors here, okay, maybe the FAMOS type of transistors, okay, and one of them has been programmed by introducing charges into the floating gate, okay, and the threshold voltage of that MOS transistor has increased to above 5 volts. Okay, the threshold voltage has become say 7 volts because of that process. Okay. Now, when you put 5 volts on the word line, okay, for this transistor the threshold voltage is less than 5 volts. Okay. So, what happens? This transistor turns on, okay, and this bit line is reduced to low, okay, bit line voltage becomes low. Whereas, this transistor, suppose the threshold voltage is 7 volts, okay, this is not going to turn on. It is as if this transistor does not exist here. Okay. So, this line voltage is going to remain high. Okay. So, by this process in a FAMOS transistor, by changing the threshold voltage, by introducing implanting electrons into the floating gate, we can alter the threshold voltage of the device. Okay. Basically, we can increase the threshold voltage of the device, so that it is this transistor does not turn on at normal gate voltages. Okay. And so, we can program the memory, okay, ourselves. That is, basically, if you want to program this here, okay, we have to apply a 25 volts on the word line, okay, and a 5 volts on this bit line. Okay. We have to we must be able to do that, okay, in which case this particular transistor will get programmed. Okay. And for all the other transistors, so although you have 25 volts, you do not apply 5 volts drain voltage here. So, it does not get programmed, all right. So, this is how you can have a EPROM. Okay. You can basically program it. No, yeah, but the point is erasable. So, I mean, what is the use of programming it if you can't erase it? Okay. You must be able to erase it and then program it. Now, what happens is, once electrons are implanted into the floating gate, okay, these electrons can stay there for many years. Okay. They and so, once you program it, the program is not lost. Okay. In fact, tens of years. Okay. I mean, you can have that program, okay, whatever you have programmed, all right. So, to erase it, what has to be done is, you have what is called a UV erasable programmable ROM. Okay. All right. Basically, what you do is, you expose the memory chip to ultraviolet light. These memories, UV erasable programmable ROMs, they come with they have a particular package, you know, where there is a window, glass window on top. Okay. All right. So, you can expose these the memory cells to ultraviolet light. Okay. So, basically, what you have to do is, you have to take this chip, okay, and expose it to ultraviolet light. And once you do that, these electrons which are in the floating gate, okay, they get excited because of the high energy they acquire, okay, and they may overcome again the silicon dioxide barrier and may move over to the silicon substrate or the control gate. Okay. And once they do that, you are basically reducing the threshold voltage again. Okay. So, it takes a lot of time, okay, maybe half an hour you have to expose it to ultraviolet light, okay, after which you the electrons move out from the floating gate, okay, and then again it is ready for reprogramming. Okay. The point here is that in this case, you cannot erase a part of the program, a part of the chip. Okay. When you erase, the entire memory has to be erased, all right. The entire memory, okay, has to be erased, and then again you have to reprogram the entire memory. It is not that if you have a part of the memory you can erase or anything. Whatever you had in the chip is removed, okay, and then again you have to reprogram the whole memory. Okay. So, that is the problem. Okay. And of course, you see that what you have to do is, in fact, you it cannot be programmed in the circuit itself, all right. I mean, basically what you have to do is, if you want to change whatever is the contents of this memory, you have to take out the chip from the circuit, okay, expose it to ultraviolet light, okay, to remove the memory, and then again you have to have a special mechanism because you have to apply very high voltages, 25 volts or so. Okay, so you have a program kit, for example, where you do the programming, and then again you have to put it back into the circuit. Okay, so basically the writing process, okay, is very cumbersome. Okay, and again, so that's why it's read only. It's basically a read only memory. Okay, you can read from it, but writing you can do once in a while. You cannot do it all the time. Okay, it doesn't make sense. Okay, so that is a EPROM. All right. So so obviously we would like to have something which is more flexible. That is, you can do the writing operation, okay, maybe inside the circuit itself, maybe, all right, or it can be a faster operation. You need not have to take out the chip from the circuit. Okay, so that type of thing led to what is called a electrically erasable programmable ROM. Okay. So this is electrically erasable programmable ROM. Okay. Now, the device which is used actually in the EEPROM is similar to this FAMOS device, but it is slightly different. It is the device which is generally used nowadays is called the FLOTOX, okay, which stands for floating gate tunneling oxide MOS. Okay. Basically the device structure is something like this. You have a floating gate again, okay, and then you have the control gate on top. So this is source and drain, N plus substrate. This is the floating gate, and then you have the control gate, okay, and then of course you have the source and drain contacts. Okay. So basically the difference here is, okay, that what you have is the drain, over the drain you have the floating gate, and here the oxide thickness is very small, okay, much less than 100 angstroms of oxide. Okay. So here if you apply positive voltage, a large positive voltage on the control gate with respect to the drain here, what is going to happen is the electrons will again will tunnel through the oxide here, okay, and will get implanted into the floating gate. Okay. And because this oxide thickness is very small here, okay, it's a tunneling oxide basically, okay, this process is going to be quite fast. Okay. And in the reverse process, okay, again if you make the drain voltage here very high and the gate voltage, control gate voltage, okay, may say 0, then you have a reverse field, okay, and the electrons implanted in the control gate, okay, can be removed, okay, through this tunneling oxide. Okay. So because this is the electric field, okay, which is aiding the tunneling. Okay. If the oxide is very thin, okay, and you have if you have a large barrier, but if the barrier thickness is quite small, electrons can tunnel through the barrier, okay, with the help of an electric field. So that is utilized in implanting or removing charges from the floating gate, okay, in this type of a system. So what you have in a EEPROM, the structure is something like this. Okay. again it's quite similar, but with a small difference which we shall see. So, you have basically a 2 transistor cell. So, this is one select line, and this is, so this one is the floating gate transistor, okay, and this one is a normal MOS transistor. Okay. So, again at every intersection you have a cell. So, this cell is basically a 2 transistor cell, okay, unlike the other ROMs which are 1 transistor cells. Okay. So, okay. So, it is something like this, okay, and of course, at every intersection you have this. Okay. Now, what is the purpose? Here you see one is the word line. You have 2 word lines in fact. Okay. You have 2 word lines. The purpose of this is, see, when you want to program the memory, okay, what you do is you have to make the gate voltage much high and the drain voltage 0. Okay. So, what you do is you have to select a particular make a gate voltage high and the drain voltage 0. Okay. Now, and when you want to erase the cell, you have to make the drain voltage very high, say 25 volts, and the gate voltage 0. Now, what happens is, if you did not have this extra transistor here, what is going to happen is, when you make the drain voltage 25 volts, okay, all the transistors connected to this particular column, okay, is going to have a 25 volt drain voltage. Okay. So, that is going to that may alter the contents of that particular memory, that may erase the contents of that particular memory cell. So, what you do now is, with this extra transistor which is called the select transistor, okay, what you do is you can select the particular transistor in a column, okay, which will have the specified drain voltage. Okay. That is, suppose you want to erase this particular cell, okay, you apply 25 volts here, okay, on this line, but what you do is you select this W prime which I have put here, okay, only one of the transistors. So, in one row, okay, one of these W prime is selected. Okay. That is, here you have a number of rows, okay, each with W and W prime. Okay. Now, only one of these W primes is selected. Okay. So, you have another cell here, say, okay. Now, when you apply 25 volts here, okay, and this is, say, this is high and this is low, okay, what happens is, this transistor is on. So, only this cell drain voltage gets 25 volts. Okay. All other cells in this column is disconnected. So, basically you increase the voltage of one particular column, okay, and you select the transistor on that column, okay, which you want to erase. Okay. So, basically what you do is you can erase a single bit of memory. Okay. Unlike the previous case, UV erasable programmable ROM, you have to erase the entire memory at a time. Okay. You cannot erase bit by bit, it is not bit erasable. Okay. Whereas this one is bit erasable. Okay. That is, you can erase one bit at a time. All right. So, that is the advantage of this, and of course, similarly when you want to program it, okay, you have to put a 25 volts on the gate, on the control gate, and only one of the cells, okay, is selected again, okay, by this W prime line, okay, here W, okay, and that means only one drain voltage is going to be 0. Other drain voltages are floating. Okay, so you can program, okay, only one of the cells at a time. Okay, so that is the advantage of a EEPROM. Although it is true that you now have 2 transistors per cell instead of 1 transistor per cell. Okay, so the density of an EEPROM is slightly less compared to the normal UV EEPROM, other types of ROM where you have 1 transistor per cell. But the advantage here is you can erase it bit by bit. You can erase one particular bit. Okay, it is bit erasable. Okay, and you don't have to take it out. Okay, you can do it internally. In fact, in many of these EEPROM chips, okay, these high voltages are generated internally, okay, by a particular circuit called charge pumping circuits, okay, which actually generate this 25 volts internally from the 5 volt power supply. So you don't have to have an external 5 volt power supply. Okay, so these voltages, because you require them just for a short interval of time, you don't require 25 volts for a long period of time. You just require it for the writing time, okay, which may be a few microseconds maybe. Okay, so for that short period of time you can generate large voltages, okay, and that is done internally inside the chip when you want to do a writing operation or an erase operation. Okay, but even then, for these EEPROMs, the writing time is much larger than the writing time or the erasing time. Okay, is much larger compared to the normal reading time. That is, if you have stored any information in the ROM and you just want to read it, that operation is very fast. Okay, but if you want to alter the contents of the memory, it will take much longer time. Usually, that is of the order of tens of microseconds. Okay, whereas the reading time may be in the order of nanoseconds. Okay, so you see that there is still a lot of difference between the time required to write into this memory, okay, and the time required to read from this memory. Okay, so that is why it is still, it still is a ROM, okay, and it's not a RAM as such. Okay, there is another type of memory which is called a flash EEPROM. Okay, this is also an electrically erasable programmable ROM which is available. Okay, that the difference there is you have a single transistor cell. Okay, you have a single transistor cell that is also electrically programmable, but in that case it is not bit erasable. Okay, when you erase, you have to do a global erase. Okay, because of this problem, if you do not have the select transistor, okay, you cannot do a bit erase. Okay, so you have to do a global erase. So this is also available, a flash EEPROM. This is a 1-bit cell, but global erase. Okay, so these are the types of electrically programmable ROMs which are available at present. Okay, so just to summarize this section on memories. So we have seen all different types of memories now: static RAM, dynamic RAM, and programmable RAM. So if you look at it, okay, the different characteristics of these memories, the desirable features which one would expect in a memory is, for example, whether the memory is, say, non-volatile. Okay, non-volatile means that is the memory contents are retained even without the help of power supply. Okay, so that is a desirable property. Okay, and of course the ROMs, okay, will come under this category, but the RAMs, okay, they are not non-volatile, they are volatile memory. Okay, then again low power. Okay, here again Okay, the ROMs, for example, they don't require any power, okay, to retain the memory. Okay, the static RAM requires much more power. Okay, the dynamic RAM requires much less power. Okay, so again you have this. See, I think so. All these things you see, basically the ROMs are having the advantage. Okay, high density. Here again, the ROMs, okay, of course the dynamic RAM with its single transistor cell, okay, is a very high density memory, and also the ROMs, okay, if you look at the EEPROM, okay, it's just 2 transistors per cell. It is also a very high density memory. Of course, the static RAM, okay, is not a very high density memory, okay, because it uses 4 to 6 transistors per cell. In system rewritable. Okay, of course here, of course EEPROMs, okay, one the newer versions, okay, one can actually do that, but it is again we must say that it is a very slow process compared to the reading process. Okay, here of course the RAMs have a greater advantage over the ROMs. Okay, so these fully bit erasable. This is of course EEPROM. Is all the memories except the flash EEPROM, okay, would have this advantage. Okay, now you see that, so basically an ideal memory, okay, would be one which has all these good properties. Okay, now of course none of the memories amongst all the memories, okay, have all these properties. Okay, so of course there is a lot of work going on to realize the ideal memory. Okay, that is, for example, maybe a static RAM, which is say for example has a single cell, a single transistor cell, okay, and is non-volatile maybe. Well, it would be an ideal memory. Or for example, an EEPROM, which can be where, okay, the writing time, or the flash EEPROM maybe, the flash EEPROM which is bit erasable, and where the writing time is as small as the reading time. Okay, or for example the EEPROM, which is again which has a longer writing time, okay, about microseconds. If that can be brought down to say about of the order of nanoseconds, okay, that would be a very good memory, because it has almost all, it is non-volatile, it is low power, it is quite high density, just 2 transistors per cell, okay, and it is fully bit erasable. Okay, so in fact, there is a lot of work going on, maybe to realize this ideal memory. Okay, so we have to wait for the future for that. So so with that, we come to the end of this section on memories, okay, where we discussed the different types of memories, okay, the static RAM, the dynamic RAM, and the EEPROM, okay, and we have seen the characteristics of the different types of memories, okay, and some of the future directions also. Okay, all right.